Look at this great doodle I've drawn here, this long, simple curve just chilling like this. But this isn't just any old curve, it's a special type of curve known as a Jordan curve. Why? Well, if you look real close, you'll find the answer. But for real, a Jordan curve is defined as one which is continuous, closed, and non-self-intersecting. So for example, these would be Jordan curves, and these ones wouldn't. Now here's a question for you. How do you package all of that information in a formal mathematical way? Well, that's where topology comes in, and we only need a few basic concepts to get the job done. Firstly, we need to kind of formalize shapes. So this right here is a disk, a closed two-ball. And as indicated by the shading, it includes the entirety of this region. Now you're probably used to calling this a circle, but it's not. This right here is a circle. Notice how it's just the boundary. And technically I lied, this is called the one sphere. So now we have our two objects, we want to know how they're related, because, well, obviously just looking at them, they look damn near identical, so there has to be some relation. What we say is that S1 is the boundary of D2, with that little delta symbol over there meaning is the boundary of. Now if this seems familiar, then you're not going crazy, because this is the symbol used in partial differentiation. And I don't think this is intentional in the slightest, but it's interesting how the rate of change of area of a circle, or D2, is equal to the length of the boundary of a circle, which is S1. Tangent aside, we now reach a definition you actually care about. A Jordan curve is a subset of R2, the 2D Cartesian plane, that is homeomorphic to S1. And now obviously the question is, what is a homeomorphism? Well, I'm glad you asked. A homeomorphism is a bijective function between two sets, or actually in our case, two topological spaces, which has a continuous inverse. If you're a little rusty, a bijection is a function that's both one-to-one and surjective, which means that each input has a unique output, and every output in the output space can be reached from some input. So that's cool and all, but how do we actually know that a homeomorphism exists between our one sphere and a given subset of R2? How can we be sure that when we move between the circle and all manner of funky shapes, we don't end up doing something that means it doesn't have a continuous inverse? Well, we can resolve this issue by introducing a final pair of terms, a compact space and a Hausdorff space. A compact space is one where every open cover of X has a finite subcover. If you know what that means, then fair enough, but for us peasants out here, an easier way to explain it is that if X is the union of a family of open sets, then there is a finite subfamily whose union is X. For example, let X be this pile of circles on the screen. If you want, imagine it to be a pile of clothes. Now currently this space is compact because we're covering the whole thing with a finite number of circles. But even if there were infinite circles, the space would still be compact because we don't need all of these, right? We can remove a bunch of circles and this right here is enough to cover the entirety of the space. And a great thing about compact spaces is that if you have a compact space, any subspace is also compact. Now technically it needs to be a closed subspace, but ignoring the technicalities, this kind of makes sense. And then we have a Hausdorff space, which is one where two distinct points can be separated by disjoint open sets. Or slightly more symbolically, for all x and y in X, which is our space, there exists some subspaces, U and V, such that X is in U, Y is in V, and the union of U and V is the empty or null set. And just like compact spaces, any subspace of a Hausdorff space is itself Hausdorff, given the appropriate T's and C's about openness or closeness, which we again deduce with a diagram. If you have this space X here, and a subspace Y, and you pick 2 points X and Y in Y, since these 2 points are also both in X, the Hausdorff space, it's possible to contain them in 2 distinct disjoint open sets, which means that in Y, it's also possible to contain the 2 points in 2 distinct disjoint open sets, so the subspace is itself Hausdorff. Now, unless you've studied topology before, it's kind of hard to come up with a non-Hausdorff space. A non-compact one is kind of easy, right? R2 is non-compact. But non-Hausdorff, I can't think of a simple one, but feel free to correct me in the comments if I'm missing one. Alright, but now let's swing back around to the matter at hand, which is proving that a homeomorphism exists between S1 and our Jordan curve J, which is a subspace of R2. To do this, we note that S1 is a compact space because, well, it's like a nice, normal, finite space. And then J is a Hausdorff space because you can always cut up your curve into 2 pieces, each with 1 point on them. And then we use the beautiful result that if you have a continuous bijection from a compact space to a Hausdorff space, then it is necessarily a homeomorphism. Now the proof here looks rather compact, pun fully intended, but it requires proving a bunch of other things, and they're all to do with sets at the end of the day, and I hate sets. Plus you've learnt the terms compact and Hausdorff, so that's good enough for me. So we've proven that such a homeomorphism exists, so we aren't going crazy, Jordan curves do exist, and they can just be defined as subsets of R2 that are homeomorphic to S1. And there we go, that's how topology can be used to formalize things that seem really obvious. There is more to this story. There's something called the Jordan curve theorem, which is another obvious statement, just saying that Jordan curves have a distinct inside and outside, and maybe I'll do a video on the proof of that at some point, but it isn't that short, so we'll leave that for later. Anyway, hope you enjoyed this cheeky little intro to topology, and thanks for watching.